approximating with finite sums first. So we know that if you had a constant velocity, so if you, set your cruise control or whatever to 50 miles per hour, and it actually stayed at that the whole time, then if you drove, these are the automated cars now, so you did that for 3 hours, then the distance that you traveled, would be just that. So the distance that you traveled would be that constant velocity times the 3 hours, and you would have gone 150 miles. So miles per hour times hours gives you the miles. Now that's true with a constant velocity, but it also is true when the velocity is not constant. That is, it's the area between the curve and the x-axis. So if you have a variable velocity curve, and you have some amount of time, then if we can find that area between the curve, between the velocity curve and the t-axis, that is still going to represent our distance traveled. So what we're going to do first is like what Newton and Leibniz did. We're going to act like we don't know how to find the exact area under the curve, and so we approximate it by making rectangles, and then finding the area of each of the rectangles, the finite number of rectangles, adding those areas up and calling that an approximation. So our book kind of makes up its own notation there, and it calls it the rectangle approximation method, which it very cleverly abbreviates as a RAM. So you're going to see this notation that they will ask you to find an LRAM or an RRAM or an MRAM in your homework. And so what they mean then is find the area using, and they'll say it like however many, something like that. So what they mean is, divide that interval into 4 subintervals of equal width, and make it a left rectangle where you're taking the left side as the height, or the right, or the midpoint. That makes sense? So it might be something like, let's say f of x is 4 minus x squared. So we'll look at that interval from 0 to 2 to make our life easy and simple. So we know that this is a parabola that opens down. It's got a y-intercept at 0, 4. It's going to cross the x-axis at 2. So we're talking about right there. So we could do, say, using the notation that you'll see, if we do a LRAM of 2, that means we're going to use left rectangles. They avoid the term Riemann sum for now. We're going to talk about that shortly, though. So they're going to say use rectangles, left rectangles, which means the left side is on the curve, and we're going to use 2 of them on that interval from 0 to 2. And so we would then imagine that we're going to take those 2 rectangles. Does that make sense? And so we would then just find the area of each of those rectangles. So we're going to have to go base times height. So since we're going from 0 to 2, that means the base here is going to be 1, and the height will be 4 because we're going to plug in 0. You with me there? Mm-hmm. Plus the second rectangle is going to have a base of 1 and a height of 3. And so we'll get 7 as that approximation to the area under the curve. Now, you'll be asked at times, is that going to be an overestimate or an underestimate? And then how do you know, or how would you justify it? So if it's an over or under estimate, you can, and I know it's really tempting to just say, well, look, see all of this stuff here means it's an overestimate because the rectangles are overhanging the curve, but on an AP question, that's not a valid justification. Why is it that that is going to be an overestimate? It's not the concavity. It's increasing, decreasing for a rectangle. The concavity matters for a trapezoid. Okay, so that's where you got to be careful. So it is going to be an overestimate, and the reason is because f is decreasing. It's not the concavity that makes that be an overestimate, it's that it's decreasing. Because it could be concave down, and we would still get left rectangles, are going to be an overestimate. So it's not the concavity piece. Okay. Now, interestingly enough, a midpoint Riemann sum is the same as averaging a left Riemann sum and a right Riemann sum, which is also the same as a trapezoidal rule. So a midpoint Riemann sum does follow the rules for a trapezoidal rule, which is concavity. That's kind of interesting. Okay. Okay. How much time do I want to spend on this? So someone in your book, I mean, if I ask you this question, it's not going to be very many of these, but I think there's a couple on your book where it might be like 8 or 10 of these rectangles, in which case entering into your calculator and summing it up there makes your life a lot easier. Do you want a reminder on how to do that? Probably. Okay. So suppose that we were going to do, well, let's just do it on this one, even though we don't need the calculator, because this way it'll go quick. Okay, so suppose we were going to do this on our calculator. So what we're going to do is we're going to go to stat, and then we're going to hit enter because we want to get to those lists. So you're going to see L1 and L2 and L3. Now yours may have junk in them, so there may be stuff left over from some earlier problem. So to clear it, remember, you're going to go up arrow into, it's called the formula bar, and then hit clear and enter, and that'll wipe the slate clean. So you want to do that. So then once you put your cursor there, if we're going to evaluate this as a left Riemann sum, we want to put into L1 the values of x that we're going to plug into our calculator, into our function, this 4 minus x squared. So in a left Riemann sum, we were going to put in 0 and 1. If it was a midpoint Riemann sum, you'd have to pick like 0.5 and 1.5. Those are a little tricky. So you can put in 0 and 1. Okay. Now our delta x's are always the same. If they weren't always the same, you might want to make a column for the delta x's, but ours are going to be the same anyway. Okay. Then what we can do here is you can go up into the formula bar. So once you're up in here, then you can put in there our function. So you would go 4 minus, and then you would go L1 squared. So it's going to take the value that is in L1, square it, and then it'll just, when you hit enter, it'll fill in that column, which isn't very impressive here because there's just 2 numbers. But if you're doing, 6 or 8 or 10, that's saving you a ton of work.
How do we put the L1 in?
So it's a second, and then somewhere in there is it second
Like
one?
everyone else is-
See it? So you find the L1. That means it's going to take whatever in L1 and do that to it. Is that okay?
Yeah.
Then, now, if there was a different delta x, you might even go to L3 and say, take L2 times whatever your delta x was. In our case, it's just 1. Okay. So we don't really have to do that. But it was something different, or especially with something variable, you might put all of the different delta x's in there and make another column. In our case, what you have in L2 is the area of each of those rectangles. So now we just want to sum that up. This is the part that I never remember what I wrote.
Stat, and then arrow over to calc, and then one variable stats.
Okay, stat. Okay, and then one arrow over to calc.
And then it's the first one,
And the very first one.
called one variable stats.
Oh, there's a one that says sum, actually.
Oh, okay.
There must be another way then. I think it is still on the calculator.
That one will sum it for you, but it'll also give you a bunch of other stuff.
Okay. Oh, there it is. So go second stat, and then right arrow to ops, I think operations, and then I think the key, I thought it was just a sum.
Under math, from that,
Math.
there is a summit.
That's what we want. Yep,
Math?
thanks. So math, yeah, go to the math part.
Second list,
So second, what was it?
list second, or second stat,
Stat,
and then math.
and then math, and then you want the sum, the thing that says sum. And then when you hit enter, it's going to wait for something, and you just tell it to sum whatever list you have. In our case, that would be just L2. And when you hit enter, it adds all those up, and that's going to be your value. All right? Well, got that section covered. Let's talk about definite integral.
We're using big words. The new section behind us.
So the idea is, in the very most general sense that we can, if we imagine we're taking some function f of x and we want to approximate that area under the curve from, say, A to B, then we could, it's called partitioning it. We're going to partition this into n sub-intervals. And we're not going to initially, in the most general sense, we're not going to assume that they're equal width. So they could be variable width rectangles. So we might pick, one sub-interval there, the other one might be wider. So I'm just trying to emphasize the fact that these could be variable width. It's called a partition. So we divide that, just looking kind of at the x-axis between A and B, dividing that up into n subintervals. Then out of each of those, we create some kind of rectangle. And here again, in the most general sense, we can pick, like on a subinterval, say from here, we could pick any value of x on that subinterval to plug into the function to get the height. So we usually talk about a left Riemann sum or a right Riemann sum or a midpoint Riemann sum, but it could be random. It doesn't have to be the same for each rectangle. In the most general sense, we're just going to find some value in that subinterval, plug it into the function, and use that as the height. And so what we get then is that we get this summation. So we're going to approximate our area between the curve, and I'm using area in a very loose sense here because you can see that if the curve is below the x-axis, then those f values are going to be negative. And so that's not really an area. Okay, it's some kind of a net area. Then it's going to be f of c sub I, and then I'm going to say delta x sub I. So for each of those rectangles, we're going to pick some points on that subinterval, plug it into the function and call that the height. and then its width is going to be different for different rectangles. So anything of this form is a Riemann sum. So it's just adding a finite number. So I'm going to say I going from 1 to n. It's adding up the area of a finite number of rectangles. And you can make that rectangle any way you like, okay, as long as the height comes from some point on the curve, and then the width is going to be that little delta x, the width of that subinterval. So that's the most general sense of Riemann sum. Now, what we want to do then, so we can say that we can talk about, some people will write, this is not really the way it's done. So I'm going to say, the limit as the delta x's go to 0 of that sum. So what we mean is, because these delta x's are not uniform, I can't just say take an infinite number of rectangles, because that won't guarantee that it's going to actually give us that area under the curve. So what's used is this expression for the maximum value of that delta x sub I. This notation is written as, it's like a magnitude of the norm, a magnitude of this delta, and that's called the norm. So what that symbol here, this weird symbol, magnitude of this delta, it's the saying that take the largest delta x that there is out of all those n delta x's. And so if we say the limit as the norm goes to 0 of this sum, if that exists, so that gives you a finite number, then we say that is that, you know, we don't call it the area, we call it the definite integral. That's actually our definition of a definite integral, which is kind of awkward and hard to work with, both conceptually and in actuality. So the vast majority of the time, so we kind of just need to know that that's what it is. But if we're really going to use it, we would usually say, to make our life easier, we'll make the delta x's be uniform in width. Then we still have, here's our Riemann sum, f of c sub I delta x. Now we don't have to call it a delta x sub I anymore, because they're all the same. And then, because they're all the same, we don't have to do this whole norm symbolism now, because since that's our delta x, if we let n go to infinity, that's going to make the width of the rectangles go to 0, which is really what we want. So now we can just say the limit as n goes to infinity. That's maybe a little easier way to at least wrap your head around it, what it means conceptually. Does that kind of make sense?
As much as it can.
As much as it can. So, if this limit exists, if the limit exists, we say f, the function, is integrable. We are expanding always our vocabulary. It's integrable. Its integral exists. We can integrate over it. You can find the area in quotes between the curve and the x-axis. Okay, and then we, have our symbolism just to refresh our memory. So this is called an integral sign. And again, it's intended to look like a stretched out S, because in some sense it's representing an infinite sum. So sum being S. So the A is the lower limit of integration, and of course that's the upper limit, and that's our integrand, and that's our variable of integration. And unfortunately, you've seen this before. before, so I think we'll be okay. All right. We're good.